Good morning. Let's do a two-dimensional conservation of momentum problem using air hockey discs. You know, like on an air hockey table?
Flippin' physics.
Billy, could you please read the problem? And Bobby, could you please translate?
A 28.8 gram yellow air hockey disc elastically strikes a 26.9 gram stationary red air hockey disc.
The mass of the yellow disc is 28.8 grams. The mass of the red disc is 26.9 grams. And the initial velocity of the red disc is 0.
I think it would be confusing if we use Y for yellow and Y for Y direction.
Maybe we should label them disc number 1 and disc number 2.
Sure, let's make the yellow disc number 1 and the red disc number 2. Billy, please read on.
If the velocity of the yellow disc before the collision is 33.6 centimeters per second in the x direction, and after the collision it is 10.7 centimeters per second at an angle of 63.4 degrees south of east, what is the velocity of the red disc after the collision?
Velocity initial of the yellow disc, or disc 1, is 33.6 centimeters per second in the x direction. So the initial velocity of disc 1 is 0 in the y direction. The final velocity of disc 1 after the collision is 10.7 centimeters per second at an angle of 63.4 degrees south of east. And the final velocity of the red disc, or disc 2, equals question mark. Let's take a quick look at the demonstration. Bo, how would you like to start the problem?
Well, the final velocity of disk 1 is neither directly in the x nor the y direction, so let's break that into its components. Sine theta equals opposite over hypotenuse, or velocity 1 final y over velocity 1 final. Multiply by velocity 1 final to get velocity 1 final y equals velocity 1 final times sine theta, or 10.7 times sine of 63.4 degrees, which is 9.5675 centimeters per second.
Negative because it's going south.
Yeah, negative because it's going south. We can do the same thing with cosine. Cosine theta equals adjacent over hypotenuse, or velocity 1 final x over velocity 1 final, which means velocity 1 final x equals velocity 1 final times cosine theta, or 10.7 times cosine of 63.4, which equals 4.7910 centimeters per second, and it's positive because it is east.
Bobby, what should we do now? Okay, it's a collision, so we know momentum is conserved. So the sum of the initial momenta of the system equals the sum of the final momenta of the system.
Momentum is a vector.
Yeah, so we need to do conservation of momentum in both the x and y directions. Let's start with conservation of momentum in the x direction. That means the mass of disk 1 times the velocity of disk 1 initial in the x direction, plus the mass of disk 2 times the velocity of disk 2 initial in the x direction, equals the mass of disk 1 times the velocity of disk 1 final in the x direction, plus the mass of disk 2 times the velocity of disk 2 final in the x direction. Because disk 2 is initially at rest, we know the velocity of disk 2 initial in the x direction is 0, so that whole term cancels out. We can subtract the mass of disk 1 times the velocity of disk 1 final in the x direction from both sides. Then we can divide both sides by the mass of disk 2 to get the velocity of disk 2 final in the x direction equals the mass of disk 1 times the velocity of disk 1 initial in the x direction minus the mass of disk 1 times the velocity of disk 1 final in the x direction, all divided by the mass of disk 2. Now we just substitute in numbers. So the velocity of disk 2 final in the x direction equals 28.8 times 33.6 minus 28.8 times the 4.7910, all divided by 26.9, which equals 30.8438 centimeters per second. Notice how, because in this instance grams cancel out, we do not need to convert our known values to base SI units, and we get the final velocity for disk 2 in the x direction in centimeters per second. Now we need it in the y direction. Bo, could you please do that?
We start with the same conservation of momentum equation, only now it is in the y direction instead of the x direction. The initial velocity in the y direction of both disks is 0, so the whole left-hand side of the equation is 0. Subtract mass 1 times velocity 1 final in the y direction from both sides, and then divide the whole equation by mass 2. We now have the velocity 2 final y equals negative mass 1 times velocity 1 final y divided by mass 2, or negative 28.8 times negative 9.5675 divided by 26.9, which equals 10.2432 centimeters per second.
Now that we have its components, Billy, could you please solve for the final velocity of disk 2?
Let's start by drawing the vector diagram. Velocity final of disk 2 in the x direction plus velocity final of disk 2 in the y direction equals the velocity final of disk 2. We can use the Pythagorean theorem, a squared plus b squared equals c squared. Substituting in our velocities and taking the square root of both sides means that the velocity final of disk 2 equals the square root of the quantity of the velocity final of disk 2 in the x direction squared plus the velocity final of disk 2 in the y direction squared. Substituting in values means that we have the square root of the quantity 30.8438 squared plus 10.2432 squared, which is 32.500 or 32.5 centimeters per second. Oh, and velocity is a vector, so we need to find the direction. Tangent theta equals opposite over adjacent, so the tangent of the angle for disk 2 final equals the final velocity of disk 2 in the y direction over the final velocity of disk 2 in the x direction. We can take the inverse tangent of both sides and substitute in our values to get the theta for disk 2 final equals the inverse tangent of 10.2432 divided by 30.8438, which is 18.3713 or 18.4 degrees. The final velocity of disk 2 is 32.5 centimeters per second at an angle of 18.4 degrees north of east.
This is our predicted final velocity for disk 2. Our measured value is 32.0 centimeters per second at an angle of 13 degrees north of east. I'd say we were pretty close. But what I'd like to know is this really an elastic collision? Bobby, what needs to be true for this to be an elastic collision?
In an elastic collision, the kinetic energy needs to be conserved.
Bobby, you are correct. Now let's determine if the total kinetic energy was conserved. Please, Bobby, start by determining the kinetic energy initial of the system.
Do we need to first convert our known values to kilograms and meters?
Yes. When determining energy, all of our units should be in base SI units. So, go ahead.
All right. Convert both of our masses from grams to kilograms by multiplying by 1 kilogram over 1,000 grams. Convert the magnitudes of all our velocities to meters per second by multiplying by 1 meter over 100 centimeters. And now the sum of the initial kinetic energies is the sum of the initial kinetic energy for both disks. However, the initial velocity of disk 2 is 0, so it has no initial kinetic energy. Therefore, the initial kinetic energy of the system is just the initial kinetic energy of disk 1. So 1/2 times the mass of disk 1 times the initial velocity of disk 1 squared, or 1/2 times
0.0288 times 0.336 squared, which is 0.0016257 joules. Which we can convert to millijoules by multiplying by 1,000 millijoules over 1 joule, and we get 1.6257 millijoules.
Hold up, Mr. P.
Yes, Bo?
Why did you convert to millijoules, and do we have to?
2 reasons. 1, 1.6257 millijoules makes more sense to me than 0.001627 joules. And 2, in my experience, students need as much practice as possible doing conversions. But no, we don't actually have to convert to millijoules.
Okay, thanks.
We also need to determine the net kinetic energy final. The sum of the final kinetic energies is the final kinetic energy of disk 1 plus the final kinetic energy of disk 2. With numbers, that works out to be 1/2 times 0.0288 times 0.107 squared, plus 1/2 times 0.0269 times 0.32 squared. And that works out to be 1.5421 millijoules. In other words, before the collision, we measured that the system had 1.6257 millijoules of energy. And after the collision, we measured that the system had 1.5421 millijoules of energy. And now we can use the relative error formula to determine what percentage of the kinetic energy was dissipated during the collision. Using the measured net kinetic energy final as our observed value, and the measured net kinetic energy initial as our accepted value, we get a change in the measured total kinetic energy of the system to be negative 5.14% with 3 significant digits. In other words, 5.14% of the initial kinetic energy was converted to heat and sound during the collision. I would say that's pretty close to an elastic collision. Thank you very much for learning with me today. I enjoyed learning.
Hold up, Mr. P.
Yes, Bo?
I think we need to discuss Movie Character Day.
Movie Character Day.
Sure, go ahead. Who did you all dress up as?
I'm Barry B. Benson from The Beam.
I'm Zoolander.
I'm Fix-It Felix.
Fix-It Felix doesn't wear a hat or overalls.
Zoolander never wore a silver
I think he did wear a silver outfit.
Mr.
love
P,
this campaign.
who are you dressed up as?
That is correct. What are you saying? I am dressed up as the movie character, Mr. P.
You are not a movie character.
Really, you do not think I am a movie character. How much time have you spent watching me on this screen?